Okay. Yeah, so let me begin with a brief prelude. So we are seeing a LLM revolution. So these large language models are changing the world, the way we work, and the way we do things every day. And yet, despite the power of these large language models, they often seem to be like pretty mysterious, and it's quite difficult to understand how or why they work. And so one reason that these sort of large language models have been so difficult to understand is that their inner workings are extremely complicated. And so it's very hard to reason about like all the things that are going on inside a language model. And so in order to better understand how they work, one of the main things we sort of would like to address is to give perhaps more tractable mathematical abstractions for thinking about them. And specifically, we want to say come up with tractable abstractions that are still powerful enough to have predictive power. So towards this, there's been like a lot of study on generally the theory of deep learning and language models, and there are some general like widespread beliefs about structure in these models. And so perhaps the two main like widespread beliefs is that somehow these models exhibit low dimensional structure and some form of linearity. So to make things a little bit more concrete, there's this like well-known manifold hypothesis that says that real data lives on some lower dimensional manifold compared to maybe the dimensionality of the most natural representation. And then there's also this notion of a linear representation hypothesis, which says that many natural concepts or features are often encoded linearly or as like linear directions in some representation space. So to give a pretty classical example, there's this famous example for word embeddings from this like 2014 paper by Levy and Goldberg. So this is a pretty famous example, like showing that if you take the word embeddings for king and queen and you subtract them, then you get something similar to if you take the word embeddings for man and woman and subtract them. And so this kind of shows that the concepts of royalty and gender are kind of linearly encoded in this word embedding space. And so another example of this kind of linearity is this notion of steering vectors, first introduced in this like Turner et al. Paper in 2023. And so at a very high level, what these steering vectors do is they show that you can add some vector to the internal like activations of a large language model that then causes this language model to have some like noticeable change in its behavior. For instance, you can like add some vector that makes the language model more evil, or you can add some vector that makes the language model say really love the Golden Gate Bridge. Okay? And so these are like different concepts that are again kind of linearly encoded in some activation space. Okay, so let me now present maybe two guiding questions for the talk today, which are first, the can we reason about linear structure for more complicated objects than just words? Can we reason about linear structure for, say, sentences or arbitrary sequences of tokens? Okay. And second, so the thing I mentioned about steering vectors is kind of very dependent on the internal workings of the model. Okay. And so can we reason about this kind of low dimensional and linear structure in a way that is, say, model or architecture agnostic? So today in this talk, as a brief preview, I'll first kind of explain a general framework that reveals some linear structure across a wide range and is applicable across a wide range of modern language models. Okay. And then second, I'll explain a simple mathematical abstraction for kind of capturing this framework and showing how this can be used to predict and reveal some pretty surprising empirical phenomena. Okay. So as a brief primer, I'll give a quick example of one example of a surprising thing you can do with our framework. And so I'll explain this in more detail later. But at a very high level, what we'll show that we can do is we can take some, let's say, target prompt, which is like the beginning of some story. Okay? And then I'll explain how you can rewrite this target prompt as a linear combination of some kind of completely unrelated sequences of tokens. Like these sequences can even be like complete gibberish, just like random tokens. Okay? So we rewrite this target prompt as a linear combination of this like random gibberish. And then we run the model on these like sequences of random gibberish, forgetting about the original prompt. So we run the model on these sequences of gibberish. And then so then you run the model on these like gibberish sequences and you linearly combine the outputs. And then magically you get essentially a coherent continuation to the original prompt. So you can see that like somehow by linearly combining these like random sequences, we're actually able to generate a coherent continuation to the original story. Yeah.
Just to understand the example, so you give these gibberish sentences as input to the model.
Yeah.
It generates some sequence, and you combine it with the same coefficient sequence into the sequence.
Yeah, so I'll explain this concretely. I'll explain like in detail what's going on later on. But this is just like a primer of like an example of a surprising thing you can do. Okay, cool. So, okay, hopefully this is interesting to all of you. So now I'll move on to like maybe the main part of this talk. So here's a brief outline of what I'll talk about today. So first I'll explain essentially how we find this linear structure in these language models. Okay. Then I'll briefly talk about kind of empirically verifying this and seeing that the structure indeed manifests across a range of models and distributions. And then I'll discuss the consequences of this linear structure, like this example I just showed. And then finally, I'll discuss kind of our theoretical framework for capturing these phenomena. Okay. So now let me begin with the first part of the talk. Okay, so let me begin with some like very like basics about language models. So we'll think about language models pretty abstractly as just sequential probabilistic models. So there's some token space, say sigma. You can think of sigma as like the space of all possible words. And then the language model M essentially defines a distribution over sequences of tokens. Okay? So a very like simple abstract definition. And now the way language models generally work is through this like kind of autoregressive generation, meaning that you generate a sequence of tokens, like one token at a time. And so this means given history, so some sequence of tokens H, then we can use this conditional probability to denote the probability that the next token is Z conditioned on the previous history H. Okay? So we'll use this notation here, this like probability of like something conditioned on H to denote the distribution for the next token. So this is a discrete distribution on a number of elements equal to the like token space size. And so, okay, as a like really basic example, so for like the history, say I love my pet, like maybe there's a 0.6 probability that the next token is cat, and a 0.4 probability that the next token is dog. Okay, so it'll be useful to, like, we won't dive too much into how language models work, but it'll be useful to think a little bit about like one of the last layers of the language model. And so the way essentially all modern language models work is they do some internal computations to compute something called this vector of Logits, and then they sample using softmax. Okay? So what do I mean by this? So given any history H, the language model computes a vector of Logits. And so this vector has dimension equal to the size of the token space. Okay? So this is a vector with essentially one entry corresponding to each token. Okay? And then, so internally you compute this Logit vector, and the next token is sampled by taking the softmax of this Logit vector, where softmax is like essentially you exponentiate each entry and then normalize so that you get a probability distribution. Okay? So essentially all language models, you first compute Logits and then sample with this softmax. Okay? And so for most of this talk, we'll kind of use the term logit and log probability interchangeably. So technically there could be some like extra normalizing constant, but we'll ignore this for most of this talk, and we'll kind of use the term logit and log probability interchangeably. And so the main point I wanted to make here is that kind of because of how language models work, it is natural to look for linear structure in this logit space, or like this log probability space. And so this is also true for like maybe more classical examples like these like word embedding examples, that also these structures are generally found in kind of a log probability space. Okay? So it's natural to look for linear structure in this logit space. Okay, so now let me begin with like maybe a simple thought experiment. So what does it mean to have a linear representation? So what does it mean to linearly represent some history H? So here's one natural sense in which we can talk about linear representations. So we can say a vector like linearly represents a history H, so psi H represents H, if first you want it to like be complete, so it like contains all of the information contained in H. So it contains all of the information in H necessary to kind of generate future tokens from H. Okay? And then second, we want this notion of linearity, which means that the future can kind of be generated linearly from this representation vector psi of H. So to be more concrete, we have the following like formal definition. Okay? So we say that this like linear representation psi is a complete linear representation if for any future there is a different embedding vector of the future, so let's say phi of f, such that the log probability of any future conditioned on the history is equal to the inner product between the like embedding of the history and the embedding of the future. And so this, I want this to be true for arbitrary futures, not just a single token, but f can be a sequence of many, many tokens. Okay? And so this is like essentially saying that the log probability of any future kind of is a linear function. The log probability of any future is kind of a linear function, like depending on that future. Okay? So any questions about this definition? Yeah.
So the mapping fee is that like be dependent on f, or is it like empirically? System mapping for all.
So phi is like an arbitrary function of f, so it just maps f to some vector. But the point is that you want for any h this. So phi is like if you fix f, then phi of f is fixed, right? And then you want this identity to hold for all h. So this is like what like linearity means, right?
But the same phi is applied for different f.
Yeah, so each f has a different phi of f. Yeah, like each f has a different embedding.
But the embedding function, the function mapping the sequences to embedding, the mapping is the same for all.
Well, I guess it's like a bit underspecified. Here, like phi can be literally any function. So I can like literally specify a different embedding for each feature here.
Oh.
Yeah. Yeah.
Is there a relationship between a linear representation and a disentangled representation?
What do you mean by disentangled representation?
So they're like for have some feature space.
Yeah.
Like the individual like components of your representation represent like distinct features. Like your face detector would be like it's an eye, and second it's a nose, that sort of thing.
I mean, I think disentangled is a stronger notion, right? Because here you can still have like superpositions where like many features like are kind of linearly dependent, right? Okay, so here we have this notion of a linear, like complete linear representation. And so here's kind of a like simple but like exponentially large linear representation. So for simplicity, let's say we only care about sequences of some bounded length, say t. Okay? And now we can define this very naive linear representation, which is just this like vector psi of h is essentially you list out all possible futures and you have one entry that's just the log probability of that future conditioned on the history. And this, yeah.
Can I ask something?
Yeah.
I understand that the functions phi and the psi are the functions of the embedding such transformers triangular? Is it correct in the basic LLMs the assumption of the linearity, or it is the simplification for your work?
I will explain how language models kind of exhibit this approximately exhibit this linear structure.
Okay.
Yeah. So okay. Yeah, I was saying. So here is like a very naive linear representation, and it's not too hard to see that this is indeed a complete linear representation based on the definitions that we just showed. Simply because for any f, we can just set phi of f to be the indicator of the entry corresponding to f, right? And so it is then clear that the log probability is equal to the inner product. Okay? So this is like a pretty trivial linear representation. Okay. Any questions? So we can also slightly modify this linear representation. So this is like the previous linear. Yeah.
So in the previous slide, you say that it is clear that it's a linear representation if I choose phi of f to be the indicator.
Yeah. So the definition I had for a linear representation of the history H is that there exists.
Psi and phi. Okay.
Yeah. Okay. Okay. So this is the previous very naive representation. So I can make it slightly less naive by breaking up this sequence-wise log probability into a sum of a bunch of token by token log probabilities. Okay. So to briefly parse what this modified linear representation is so I have this fixed H. And then I enumerate over all possible features f of up to a given length. And then the entries are the log probabilities of the next token conditioned on the sequence H concatenated with f for all possible features f. Okay. The sort of dimensionality of this vector is the size of the token space times the number of f's. Any questions? And I claim it's also not too difficult to see that this modified representation is also a complete linear representation. And this is just because for any future, we can kind of break up this log probability using the chain rule, right? So we can just write this as a sum of token by token log probabilities. Okay? And then each of these log probabilities, you can just kind of select the corresponding entry. So the corresponding embedding of f just selects the corresponding, it's just one on the entries corresponding to these log probabilities that you want to select. So this modified kind of token by token thing is also a complete linear representation. Okay. So I still haven't said anything too interesting yet because this representation that I showed, it still has exponentially large dimension. Okay? But nevertheless, this will be an important object throughout the talk today. And so the next important observation is that we can get a lower dimensional linear representation if all of the vectors psi of h live in some lower dimensional subspace, right? And the reason for this is pretty simple. So if there is some lower dimensional, say d-dimensional subspace that contains all of these vectors psi of h, then an alternative, much smaller linear representation is obtained by simply for every h, you only keep track of the coefficients to write psi of h as a linear combination of these basis elements. Okay? So this gives you a d-dimensional representation instead of the native dimensionality of psi of h. Okay? Any questions? Okay. And so yeah, so if we had this property, then this would give us a d-dimensional complete linear representation. And so, okay, so the main takeaway here is I just want to say this kind of much lower dimensional representation exists if and only if the matrix whose rows are given by these vectors psi of h is low rank. Okay, so we can make this a little bit more formal. So recall here are the vectors psi of h. And then we can define a matrix that essentially just arranges these vectors as rows of the matrix, right? So, okay, we have some subset of histories h, some subset of futures f, and then we call this the extended logit matrix, which has rows indexed by the histories, and then columns indexed by the possible next tokens, and the possible the columns are indexed by a next token and a future, and the entries are the log probabilities as shown. Okay? So this like essentially just arranges the vector psi of h as rows of this matrix. And so the point is that we'll get like low dimensional, like much more compact linear representations if this extended Logit matrix is low rank for all possible like sets H and F. And so I'll briefly note that this is kind of convenient in the sense that this representation depends only on the logits, like kind of the input-output behavior, only the logits of the model, and doesn't really depend on any of the internal architectures like internal activations. Okay, so let me briefly comment on the relation of this object to some things people have previously considered. Okay, so here's the definition of the extended Logit matrix again. Now, there's a kind of simplified version of this object, which I'll call the single token Logit matrix, that has kind of been well studied in previous work. And so the single token Logit matrix is obtained by setting the set of Fs to just be the empty future. And so what this means then is sort of this single token Logit matrix just has rows indexed by histories and columns indexed by possible next tokens, right? And the entries are just the log probability of the next token conditioned on the history, right? So this is just like stacking the Logit vectors as rows of the matrix. And so if you think about the way a large language model works, so the last layer of the language model involves the following operation. Okay? So you take some hidden state V, you linearly embed it in like the space of logits. So the hidden space generally has lower dimensionality than the number of possible tokens. So kind of you like map from a low dimensional space to a higher dimensional space, like linearly through some embedding matrix W, and then this gives you your logits. Okay? And so like just from this, like operationally, you can easily see that the single token Logit matrix has rank actually bounded by the embedding dimension, rather than the token space size. So it is like kind of a little bit low rank at least. So this has been termed the softmax bottleneck and has been studied for both like designing new architectures and has had applications to things like security and model stealing. Okay? So this kind of single token like low rank structure has been well studied. But the main reason for considering like our version, the extended Logit matrix, is that by incorporating this like additional feature that you concatenate with H, our extended Logit matrix allows us to reason about longer sequences of tokens. Okay? So the single token Logit matrix only allows you to reason about the next token, but here we'll be able to reason about much longer sequences of tokens. And I'll actually like kind of explain how the information in the single token Logit matrix is actually insufficient for being able to reason about longer sequences. Okay? Any questions? Okay, cool. So, okay, now we have kind of the key object that we want to think about, which is this extended Logit matrix. And so now I'll talk about kind of empirically verifying the low rank structure in this extended Logit matrix. Okay. So, let me briefly explain our experimental setup. So, there are like exponentially many possible histories and futures. So, like we cannot list out all of them, but what we can do is we can essentially like subsample this matrix. Okay? So we subsample some set of H and F from some distribution. And okay, because the token space is also huge, it's like 100K for modern language models, we'll also like kind of subsample this token space down to some like smaller size. But this is like not too important. Okay? And then, okay, so for some sense of scale of like what we're going to compute, so we're going to sample essentially like 10,000 different histories and futures. And the lengths will be like, say, between 0 and 50 tokens. Okay? And then we compute essentially this subsampled version of the extended Logit matrix. So this is like the same matrix as before, but just like with like this subsampled set of entries. And okay, so we'll analyze the spectrum of this subsampled extended Logit matrix. But before looking at the like empirical like results in the plots, let's take a moment and think actually like a priori, like should we expect any interesting structure from this kind of matrix? And so one thing to observe is that kind of these histories and futures are kind of mismatched, right? So this like string H concatenated with F can often be kind of nonsensical. It's like a history about one thing and a future about another. So maybe it's like not so clear that there should be any interesting structure in this matrix because these kind of sequences may be like way out of distribution. Okay, but nevertheless, we see that for modern language models, this extended logic matrix does have low rank structure. So here's an example plot for the language model like OMO 7B. And so here H and F are sampled from Wikipedia. And so here we see, so this is a log-log plot. So we see that the singular values exhibit a power law decay. Right? And so this is like very much not random because a random matrix like definitely does not have this kind of power law decay in its singular values. And so furthermore, like you might notice it's like kind of like these downsampled like headers. And so what this downsized thing means is that essentially if we subsample the matrix to a smaller matrix, the spectrum kind of remains consistent and scales like appropriately. And so this is essentially like verifying or like strongly indicating that the like low rank spike that we see here is actually consisting of kind of some global low rank spike in the very large extended logic matrix. So this is like some global low rank spike as opposed to just some noise. And if it remains consistent as we like increase the size of our sample, so this suggests that it's like kind of a global phenomenon that we're capturing. Okay, and so we can also verify that this kind of same phenomena holds across a range of models and different data sets. So here we can draw the same plots for two like other like language models. So for Gemma or Llama, we see like we have essentially the same behavior. And then we can also like consider what happens when we change the data set. So here we can like instead of Wikipedia, we can use a different data set like C4, which is like some like web crawled data set, or some starcoder, which is just a coding data set. We see that we still have kind of essentially the same behavior. Yeah.
Just to be sure, what does it mean that downsides?
Oh, so okay. Let's say I start by sampling like 10,000 H's and F's. So I can also consider sampling like 5,000 instead, or like 1,000. And what I'm saying is that like no matter the size, kind of the spectrum is consistent. So this suggests that it's kind of like a global phenomena as opposed to noise. Yeah. As you increase the length of the features, the decay, like the rank increases a little bit, but not much. Yeah. Okay, so yeah.
Something similar has been observed for deep neural networks way before LLMs. Right? So why is this surprising now? Yeah, I mean,
are you talking about this like?
Decay, but also this exactly this behavior in singular values, right?
So you're talking about like this paper that is like why are big data matrices approximately low rank or something?
No, I'm literally remembering something from my PhD back when LLMs didn't exist, where like I could literally discuss the same plots. Right? Like, it has been known for several years that even ResNet 50.
Wait, sorry, are you looking at the weight matrices? Or I mean, one thing that's different here is that this is like not the internal weights, right? Like this is like the actual input-output behavior of the model.
Sure. So I'm saying the same thing.
Okay.
It's like it's so that's my question. Why is it surprising now, and how does it compare with like ResNet 50 or all these other pre-LLM models?
I think maybe I'm not trying to say that this is particularly surprising now, but I think maybe what is surprising is like the things that you can do with this structure. I think like maybe it's like a priori not obvious that the structure should exist, and then I'll explain like some like interesting things that you can do with it. Okay. So the first thing that towards like understanding what we can do with it, let's maybe go back and think a little bit more about like what does this kind of like approximate low rank structure mean? Okay. So like when the matrix is approximately low rank, it means that they're kind of like approximate null vectors in the column space. So there's some vector that we can like multiply on the left such that the result will be approximately 0. And so in other words, this is saying that there is some like linear combination of these like linear representations that's approximately 0. And So in other words, what this is saying is that the approximate null vectors in the column space describe the linear relationships between different histories. So if I have a linear combination that's 0, then this is saying that these histories are kind of linearly related according to the coefficients in this linear combination. And so the earlier example is like maybe a very simple instantiation of this, that like these single words, there's like this linear relationship between them. But the thing we're doing here is we're able to express like much more complicated linear relationships between much longer sequences of tokens. And so now we might wonder like how universal are these linear relationships? In particular, do they transfer like A across models and B across different distributions? Any questions? Okay, so first let's discuss this like possibility of transfer across different distributions. Okay? So we can consider essentially constructing this matrix, this like extended Logit matrix for, let's say, the same set of H, but for F, two different sets of Fs drawn from two different distributions. Okay? So we can consider first a distribution of Fs that is kind of like in distribution, say drawn from Wikipedia. And we can consider a second possibility for sampling the Fs as just like literally random sequences of tokens, so complete gibberish. Okay? And then to essentially see how much the linear relationships transfer, we can compute the principal angles between the, say, like top k column subspaces for various values of k. Right? And so this like principal angles between these subspaces measures kind of how overlapping these subspaces are. And recall the column space essentially corresponds to linear relationships between the different histories. So overlap between the column spaces is like saying the linear relationships transfer across distributions. And so we see in the following plot that sort of the top k column subspaces have a lot of overlap for various different values of k. So the dashed line is like a baseline for if the subspaces were random. And so we see that, okay, these subspaces are very much not random. And in fact, the fact that these lines are like so close to 1 means that actually these subspaces share like a pretty high dimensional, like almost k-dimensional, like common subspace between them. And so what this means is that actually even replacing the distribution for F with like complete gibberish, like complete random sequences of tokens, you can still reveal essentially the same linear relationships between the different histories. And so I think this is perhaps like at least somewhat surprising because these like random sequences of tokens are like way out of distribution, right? Like the model's like never been trained on just like random garbage. And yet like through like looking at the model's logits and outputs on these like kind of random sequences of tokens, you can reveal kind of the same linear relationships between the different histories. Okay? Yeah.
Can you understand what, like the cosine, I understand when I am going to one is fine, but what is the index? Like I'm trying to understand the plot.
Oh, so the rank is just like different values of k. Or what are you asking about index? Oh, sorry. Oh, so
the x-axis.
Oh, okay. So yeah. So when you take two subspaces, I have like two matrices, let's say U and V, corresponding to two subspaces. I look at the singular values of UV transpose. Okay? So there should be, like if the two subspaces are both k-dimensional, then there'll be k singular values. And so if they're exactly overlapping, then this will be identity. So it'll be all ones. And so sort of like the number of like the amount or the length that the like plot is kind of like at 1 is essentially saying that there's like essentially a like shared subspace contained in both of these subspaces of that dimension. So like the fact that these lines are like close to 1 like before the end is essentially saying that these subspaces have a lot of overlap. Does that kind of make sense? Okay, I mean, like the exact construction is like not super important. I guess all I'm saying here is that you can verify that there's a lot of overlap, even as I like completely change the distribution for F. Yeah.
Let me try to create that plot again.
Yeah.
So I see some line dropping down. While you're happy when the line goes to 1 because that means 0 angle and that means that they're aligned.
Yeah.
So what is the evolution of each plot? This is what I'm trying to understand.
Oh, So when I compute the angle between two k-dimensional subspaces, you're going to get k principal angles. Okay, and so most of those will be 1, but like the last couple will be like smaller because maybe there's like one vector that's in one subspace and not in the other. And so that'll give you like a like the last principal angle might be 0, or sorry, it might be like 90 if you have like one vector that's in one subspace but not the other.
Okay.
Yeah. So it's saying that like the subspaces have a lot of overlap, but like maybe towards the end they have like a couple like different vectors in them. Okay. So next we can also ask this question about like transfer between different models. Okay? And so here we can like compute the same matrix for the same h's and f's, but for two different models, M1 and M2. Okay? So here we'll do this for like Olmo and Gemma. And we can essentially plot the same kind of plot and see that the sort of overlap is not as strong, but it is still like certainly like very non-trivial. And so this is essentially saying that the different models kind of share similar linear representations between the different histories. Yeah.
So when you are saying rank 10, how
Yeah.
are you sure that this is rank 10? How do you?
Oh, sorry. Like rank means like the value of k. So I'm just computing the angle between the top like 10 dimensional principal. Like I'm taking the top 10 PCA of these two, and then I'm computing the angle.
The first 10 eigenvectors and eigenvectors.
Yeah. I'm taking the first 10 eigenvectors of the two matrices, and then I'm computing the like the overlap. Yeah. I think the main point I want to illustrate here is that there's clearly like a very high, very non-trivial amount of overlap in the linear representations kind of do transfer. Okay, so next, I hope I can convince you that this kind of low rank structure does exist. So now let me try to explain what can you do with it. Yeah. So to understand what you can do with this kind of low rank linear structure, let's go back and kind of think about these linear combinations again. Okay? So recall we have this embedding vector psi of h. And so if the rank is exactly d, then we can write any history as a linear combination of, say, d basis histories, right? So we can write the embedding vector for any history as a linear combination of these d basis vectors. Okay, but then what does this mean? So this means that for any future, we can write the log probability of that future conditioned on this, say, target history as a linear combination of the log probabilities conditioned on these different basis histories. Okay, so this leads to the natural question: can we actually generate a sample from the target history by essentially running the model on these potentially unrelated basis histories and linearly combining the outputs? So this is the question, and I'll explain kind of going back to the experiment that I showed at the very beginning that we can actually do this. We can essentially do this generation token by token. We can essentially generate a sample condition on h by kind of ignoring h and just running the model on these kind of unrelated histories and generating token by token.
Yeah. So there's a question.
Yeah.
It says, I quote, you mentioned the why are large matrices approximately low rank paper? Mm-hmm. How much does the theory in that paper explain the phenomenon you observed?
How much?
You want to do it again?
No, I understand the question. I think it's a bit hard to say. I think I would say not so much, just because of the setting and the assumptions in that paper. Yeah. Okay, so in light of this, now let me explain how we can essentially generate with this linear combination. Okay. So we have the following generation algorithm. Okay. So we take our model, we have some basis histories and coefficients that we want to linearly combine them with. Okay. And so what I'm going to do is I'm going to first run my model on these kind of basis histories, and for each of them I get a logit vector L sub I. Okay. So these vectors L sub I have dimension equal to the token space size. then I linearly combine these logit vectors, right? And then I sample by taking the softmax of these linearly combined logit vectors. And then I append this token to all of the basis histories, and then I repeat from the first step. And so, so this entire operation samples one token, then I append it to all the basis histories, then I can repeat this again and again. So we can run essentially T iterations of this if we want to generate T tokens. And so, like, an important observation here is that if this linear combination held exactly, then the procedure I'm describing here, this linear generation procedure, exactly samples from the right distribution conditioned on the target history H. And I think this is like not too difficult to see just by like reasoning about the linearity.
Is it an effort to make distillation of the model, like linking?
Is it? I think it's not explicitly trying to do distillation, but I think that's like a potential like use of this. I think this is just like a pretty interesting like scientific phenomenon on its own. The fact that you can just like run the model on like unrelated things, like linearly combine the outputs, and you'll see a coherent response to your target. Yeah.
So you mentioned about like for different models, you're linear representations are like
yeah.
Is it possible like run like different models different?
Yeah, that's a good question. We haven't tried that, but I think that's a very natural thing to try. Yeah. Okay, so yeah, so we're actually going to run this. So okay, we first like essentially solve for this linear combination by like approximating these vectors by say subsampling and like computing some of their entries. Okay, so we solve some regression problem for this linear combination. Okay, and then we generate with our algorithm. So called algorithm, just you have your histories, you run the model, you get logits, you linearly combine the logits, then softmax you sample, and then append this token and keep going. And so the earlier example was exactly like one like small instantiation of this, where we take essentially some tiny stories model. So this is like some very simple language model trained on like very basic English. And so we fed it like this like target history. And then we rewrote this target history as a linear combination of 2,000 essentially like gibberish, like sequences of random tokens. And then we ran like 20 iterations of this algorithm with this like kind of linear combination generation. And we generated this like pretty coherent continuation to the target history. And so, okay, we can do some like slightly more like, let's say scientific like evaluations of this. So we take a slightly larger model. So we take Olmo 1B, and then we generate like a very large number, say 40,000 unrelated. So on the left, we're going to use unrelated, but still like coherent histories. So let's just say we sample like Wikipedia excerpts from something completely unrelated to the target. So these are like real looking sentences, but are kind of unrelated. Okay? And then on the right, we use like complete gibberish, like complete like random garbage sequences of tokens. Okay? And then we run our linear generation procedure and compute the KL divergence to like each token, we compute the KL divergence to what the true model would have predicted. So you can see the plots here. And so let me briefly comment on these various benchmarks. So the red line is like an earlier checkpoint of Olmo. So the red line is like already a pretty good language model. Okay? The orange line is what you would have gotten if you only used the single token logit matrix. So kind of the orange line shows how it's like clearly insufficient to only look at the single token logit matrix. And the green line is essentially if I like truncated my history to only have some shorter length. So I'm only using, say, the 5 most recent tokens. And so what this is saying is that really like our linear generation procedure is really generating coherent text and meaningfully using information from the history, even say several tokens back. Okay. Okay, so let me I'll conclude by like talking a little bit about the theoretical framework for kind of capturing this linearity. So okay, let me skip this since I'm a bit short on time, but there is some like kind of like renormalization of the logits where you like kind of change the normalizing constant a bit, That's important for making things like theoretically tractable. But now, okay, so let's consider let's go back and consider this like extended logic matrix again. And so specifically, we'll consider now the case like theoretically when this like extended logic matrix is exactly low rank. So it has like rank at most D. And so now we ask the question, are there clean generative models that can kind of capture this low logic rank phenomenon? And so the answer is yes. And so actually, we'll show that this kind of exact low logic rank is captured precisely by this notion of an input switched affine network, which is architecture that was introduced in kind of this one-off paper in 2017 in the like maybe heyday of recurrent networks before like transformers really became a thing. Okay? And so the definition of an input switched affine network in ISAN is as follows. Okay? So you essentially have one D by D matrix for each token, and then one like readout matrix B, okay? And say some initial D-dimensional state. And the ISAN works by generating a distribution over sequences of time steps as follows. Okay? So you sample a token according to softmax of B times the hidden state. So this is kind of the linear readout. And then you have a linear transition based on the token that you sample. Okay? So it's like an extremely like mathematically simple generative model where you essentially have some like linear state update and some linear softmax readout. Okay, so yeah, this is like some extremely clean mathematical abstraction, but I'll actually show that it's both theoretically tractable and like it's not like a great language model by any means, but it's actually like a pretty good empirical approximation for such a like mathematically simple model. Okay, so first, the like main reason we're like led to think about this like ISAN model is the following equivalence: that a language model having logic rank exactly D is exactly equivalent to expressibility as an ISAN with hidden dimension D. Okay, and so one direction of this is like so the interesting direction is showing that like low logic rank implies expressibility as an ISAN. The reverse direction is like not too difficult if you just like think about the definitions. Yeah. Okay, so maybe I'll briefly sketch out the proof. Don't worry if like some of the details are not super clear. So to prove this equivalence, we essentially consider a set of basis histories that kind of span the low-rank D-dimensional subspace. And then we construct an ISAN whose hidden state stores the coefficients in the linear combination that express your current history as a linear combination of the basis histories. So the hidden state kind of stores this linear combination. Okay? And then, okay, so then to sample, it's pretty easy that you can just like kind of linearly combine the logic vectors for the like basis histories, and then this will give you the like probabilities for the next token. And then to do the state update, essentially what you do is you do kind of a change of basis operation. So when you concatenate the next token, you still have the same linear relation, but you need to re-express the right-hand side in terms of your original basis histories. Okay? And so you can do this by essentially explicitly computing this like change of basis matrix that depends only on this token Z. Okay? And so, okay, you can essentially explicitly compute this change of basis matrix, and this tells you exactly how to update the state to change the basis back into this like original basis of like H1 through HT. So like very like brief intuitive sketch of why these two notions are equivalent. Okay, so this is just summarizing why these are equivalent. And now finally, as a learning theorist, let me briefly comment on this question of learnability. So given this equivalence between low rank and ISAN, there's this natural question: given a low logic rank model M, can we actually like efficiently extract out this ISAN representation? Okay. And so the answer is it kind of depends on the learning setting. And so in kind of a standard learning setting, where you're given just samples from the distribution or language model M, it's actually computationally hard. And this is because this ISAN can express any noisy parity. So under standard cryptographic assumptions, it is hard to learn from samples. But what about kind of an active learning or like a query learning setting? And so what we show is that actually you can learn an ISAN with queries of the following form, which we call logic queries. So we allow the learner to make logic queries by querying some arbitrary history H, and then they receive the logits for the next token conditioned on that history. And so I'll note that this is actually like a pretty well-motivated practical setting for say model stealing and other kind of security attacks, because this is literally the model that a lot of APIs give you. You can query some arbitrary sequence and they'll give you the logits for the next token. This is literally the model that people give you in practice, and actually has led to kind of some vulnerabilities to model stealing attacks. And so what we show is that you can learn an arbitrary ISAN via these kind of logic queries. So there's a polynomial time algorithm for extracting this ISAN representation. And actually, it's perhaps not too difficult to see how the proof should go, because it kind of mirrors the proof that I just gave you for why this expressibility result, why ISAN is equivalent to low logic rank. You kind of just carry through those steps and make it an algorithm. And so, okay, so again, I'm not saying that an ISAN is a good language model, but for something so mathematically simple, you can actually generate pretty reasonable stories. So here's an example of, so I took this tiny stories model and I learned rank 2000 ISAN from it. And so here's an example generation. Okay, so it's you can read the story. It's pretty good for a model that's just fully linear and only doing matrix multiplications. Okay. So okay, now I'm running out of time, so let me briefly conclude with some closing remarks. Okay, so to summarize, the sort of main point of today's talk was we find this kind of linear structure in modern language models through this kind of extended logit matrix. And the structure seems to be consistent across different data distributions and models. And we can exploit this linearity for generation in pretty surprising ways. In particular, we can do this linear combination procedure to generate using a linear combination of unrelated or completely nonsensical sequences. And finally, we showed that this kind of low logic rank definition implies this kind of clean mathematical abstraction for thinking about or perhaps approximating language models. And so, okay, I'll just put some new directions on the slide, and I'll conclude there. Thank you.
I have a few.
Yeah. Okay.
So one is very minor. So you said that understand the cryptographic assumptions.
Yeah.
Noisy parity is hard to learn.
Yeah.
Isn't the assumption itself the status of noisy parity?
Yes.
So it's not that there is a different assumption.
Yeah, it's literally just hardness and noisy parity. I mean, I guess I said that because maybe it's not clear to everyone that this is a standard cryptographic assumption. So.
The other question that I have is with respect to the queries. So
yeah.
With the net theory literature,
yeah.
there is this model where you allow arbitrary queries.
Yeah.
And they're slightly weaker versions of this.
Yeah.
So the queries have some more natural properties.
Yeah.
So do you need the full power of queries for this result, or would it be sort of strengthened to work with the weaker model?
I think strengthening it is a natural question. I will say this model is a pretty reasonable model. I can literally take an API, I can query some arbitrary prefix, and it will give me the logits. So this is literally a model that exists in practice.
Even for the conditional queries, right?
Yes, yes.
Similar versions, queries and more natural.
I think I'm just pushing back against the fact that you're saying this is not natural. This is literally a model that I can in practice I can literally get the logits for these APIs. Yeah, yeah. In fact, there is this pretty well-known paper that does a model stealing attack where they essentially learn the embedding dimension and the last layer using these logic queries. So it is like literally like a model that people use.
All right, so let's take this video again.